Hey everyone, my name's Alex Condello, and I'm the manager of applications development, technologies, and tools at D-Wave Systems. I work on a bunch of things with my team. The first of them is we work on the open source tools, Ocean, that D-Wave and our clients use to access the quantum computer. We work on hybrid algorithms, so combining the best of quantum and classical together. And then we work on applications, so partnering with individual groups or companies or research groups to help them solve problems with the system. Today, I'm going to be talking about all of these different things and how you use the D-Wave system and our Leap platform to solve practical problems for business. I'm also really excited to be talking to you all today because we've recently released our new Advantage system. This is our 5,000 qubit, 45,000 coupler system that is built from the ground up with practical problems and business in mind. We have built this system to be larger and more complex and to solve denser problems based exactly on the sort of feedback that we got when we tried to solve practical problems using our system. That said, these systems, these quantum computers, when simply on their own, are probably too complex for the average user to access. So you need an environment, you need a platform, you need documentation, you need examples, you need authentication, you need all of these different things. And so today, I'm going to be focusing mostly on how Leap and hybrid and the quantum computer all come together to be able to solve practical systems. And with that, I'm going to be doing, they say that a demo is worth 1,000 slides. So I'm going to be actually doing a demo today. So right here where I've started, you can see our Leap dashboard. This is sort of the first page that you would see when you sign into Leap. And I won't unfortunately have time to go through all of the different little aspects of it, but I'm just going to highlight a couple of the quick ones before jumping into some of our examples. So, when you sign in, you can see things like how much time you have available. So for free, right now, you could sign up to Leap and make use of and get a minute of QPU time and 10 minutes of hybrid solver time. You can see problems that you've submitted. You can see which solvers you have access to. So by default, I'm actually signed in with like my personal Gmail account. You can get access to you can see what a typical free user will have access to. So that's an Advantage system, a 2000 Q system, and 2 hybrid solvers, our hybrid binary quadratic model and our hybrid discrete quadratic model. So this is all available if you start anytime signing up for Leap for free. But I really want to start, giving you a sense of what type of problems that we solve with this system, and what types of problems, you can use our system to explore. So let's pop over to our interactive demos, and specifically our signed social network analysis. So signed social network is a particular type of optimization problem. Now, we're really interested in these optimization problems, and I think a lot of the businesses are as well. So let's go ahead and pop in. One of the problem that I want to look at, I think will be familiar for a lot of you, which is I'm going to be looking at signed social networks in Romeo and Juliet. So I think almost everyone here is probably familiar with Romeo and Juliet, but just to remind you, you have a collection of people, the Capulets and the Montagues, and they have what's called a signed social network amongst them. That is, they have 2 types of relationships: friendly relationships, denoted by these green edges, and hostile relationships, denoted by these red edges. What I would like to do is divide this network into 2 groups, maybe say divided by a river, such that there are only hostile edges across the river and there are only friendly edges on either side of the river. Now, this is a complex type of network. You have this sort of nuanced relationship, both positive and negative. And even though there's tension in this network, is in some sense balanced. This is called a structurally balanced network. Now, I'm going to introduce a wrinkle, which is that Romeo meets Juliet. And this actually creates quite a problem, because as you can see here, there is no way for me to divide Romeo from Juliet in such a way that I'm not violating one of the rules of my problem. I can't put them on 2 sides of the river such that there's only hostile relationships across the river. So in this case, Romeo and Juliet have a friendly relationship across the river. And in this case, Juliet and Lord Capulet have a friendly relationship across the river. So this is called imbalance. And specifically, the optimization problem that we're trying to solve here is to take to find the assignments to each side of the river that minimizes the imbalance. And these imbalances are called frustration. These edges that don't satisfy our condition are called frustrated edges. And those are important. We'll talk about why in a little while. But first, I want to mention, why do we care about this problem? Well, this is actually really close to the problem that our quantum computer solves natively. So you can represent each of the different actors in this play as a qubit. And then the couplers can define the interactions, the social interactions between them. So if you have a hostile interaction, the qubit will try to force the qubits in, or the coupler will try to force the qubits into opposite configurations. If you have a friendly interaction, the coupler will try to force the qubits into the same configuration. And so this is, again, there's a lot of sort of problems you can think about: icing, QUBO, weighted two-set. I mean, there's lots of different ways to represent this one, but this is one of the ways you can think about the native problem, the icing problem that our system solves. Okay, so Romeo and Juliet is a fun example, and it's easy to understand, but you might be asking, is this thing practical? Does this have any real-world implications? What can we use this for in the real world? Well, Nakamura et al. Did a study that showed that if you look at the signed social network amongst gangs in Los Angeles, that the degree of violence is strongly correlated with the amount of imbalance with the network. And this makes some intuitive sense because, as I said, even though there's hostility, when you can evenly divide it, it's in some sense stable. When you can't get that sort of stable interaction, when you have these frustrated edges, that's where problems can arise. More recently, some of our friends at Los Alamos National Labs applied the same methodology to the Stanford Militants Mapping Organization, which looked at violence amongst groups in the Syrian theater. So let's go ahead and take a look at that. In Syria in 2012, as you can see, there was a nice balanced network. So there was hostile and friendly relations, but overall it was balanced. However, starting in 2013, the network got quite a bit more complicated. And let's actually run this problem live on the quantum computer. So I just ran that on the QPU on our new Advantage system. And as you can see from the solution here, some hostility, some frustrated edges have started to creep into the network. So by using the quantum computer, we can access even more complicated networks than this, larger and larger networks of increasing degrees of complication, and we can try to determine how imbalanced they are and therefore how much tension there is in the network. I'll also mention that, I mentioned these frustrated edges as being important, and the reason that they're important is because this is exactly the sort of conditions under which the quantum computer can provide value. These frustrated edges are where quantum annealing can provide different annealing paths relative to, say, simulated annealing, and these highly frustrated problems are exactly the sorts of problems that we use to benchmark classical computers against the quantum computer. So I'll also mention that this problem, this signed social network problem, is highly related to a couple other problems that are also very much in the optimization space. So things like the maximum independent set problem, which you can use for, say, finding non-interacting drugs. You can also think about maximum cut for looking for communications network resiliency, and graph coloring, which is maybe, say, doing frequency analysis for cell towers. These are all different forms of the same basic problem that you can use our system fairly natively for. Okay, so there's other example, there's another interactive demo we could go through, but I actually want to address a question, which is, okay, signed social network, you've explained why it's relevant to the quantum computer. You've also shown that it has some relevance to the real world. What about solving truly enormous problems with thousands or even up to 1 million variables? Can you access that? And the answer is yes. So I want to pop over to another set of examples. So this set of examples that are available in Leap and on GitHub are a growing set of examples that we've written to show how we use the quantum computer and our hybrid algorithms to solve different problems that are relevant to industry. So let's go ahead and open up that exact same problem, the structural imbalance. But this time, I'm going to be loading this up in our online IDE in Leap. So one of the things that we've discovered is that folks who want to get started with quantum computer often have a little bit of trouble understanding, what's the right environment? What do I need? What type of tools do I need to access a quantum computer? And so we decided to put an online IDE available in Leap that has everything pre-installed and available for you. So this has Ocean pre-installed, this has scientific computing libraries pre-installed, it has your configuration to the quantum computer pre-accessed. This is a fully featured Python IDE that has everything you need to get started on programming the system. And so let's actually go ahead and take a look. This is actually the code that we're going to run. And this has essentially the same structure. This is basically identical code to the one that underpinned that illustrative demo. But this time I can interact with it, I can make changes, I can import my own data set, I can do whatever it is I want to make this relevant to me in a full-featured Python environment. So let's go ahead and actually run this demo. But the thing that's going to be different this time is I'm going to be running it on hybrid. So this time I'm going to actually use the entire world's data set, not just Syria. And I'm going to be using hybrid, which is an algorithm that uses both classical and quantum resources together to access large problems and to use the best of both worlds. So it'll be using classical for the things that classical are good at, and it's going to be using quantum for the things that quantum is good at. And let's go ahead and take a look at the result of that. So now you can see the image is a little less pretty because this is now just pure Python code. But I'm now able to access a really large network. Instead of looking at maybe 20 different nodes, I'm looking at hundreds. And in fact, we picked this size because this is something that I can run, right now in a couple seconds. But this is actually, our hybrid solvers can actually support networks of up to 1 million variables. That's a huge, huge network and very complicated. And so you can actually access these sort of problems at a fairly limitless scale. I mean, 1 million is very, very, very large. So I also want to emphasize that by using these hybrid solvers, you're having a lot of the trickier aspects of using a quantum computer handled for you. So we're doing things like tuning the chain strength, and we're picking nice energy scales and all of these different things that just abstract away these complications from you, the user, and put them into hybrid. So you're getting the best of both worlds, but quantum computers are still available. If you're interested in accessing them directly, you absolutely still can. We want to enable both pathways. And we also have a library that unfortunately I won't have a lot of time to talk about called D-Wave Hybrid, which is a library that's designed for building these hybrid algorithms. So if you want to explore building your own hybrid algorithms but use the quantum computer directly, you can also do that. Okay, so now I've talked about a problem that can be solved on the quantum computer. I've shown that it's relevant, in the world, and I've also demonstrated how you can solve this problem at true customer worldwide scale using hybrid algorithms. So the next question you might be asking is, okay, you've shown me one problem. Are there others? Are there others that are maybe more relevant to my business? So the next one I want to talk about is resource distribution. So I want to mention that this is also running out of our online IDE. I've simply spun up this environment. Here's the code all available. I've run from the terminal, but it has a GUI interface, which I'm going to go ahead and pop over to because it's a little bit nicer. But this is all being run out of our online IDE and making use of our online hybrid solvers. So the problem is this. Imagine I have a set of resources, both in surplus and in shortage. And say I have a set of hospitals and they have a set of beds. Some hospitals have surplus beds, some hospitals have a shortage of beds. I would like to take this set of hospitals and put them into small pods, such that each pod has a net surplus of beds, but such that these pods are not too difficult logistically to manage. So I'll explain a little bit more. I'll give a nice visual of what that means in a moment. I'll mention that this demo has all of the math available for how we actually do this formulation, but let's go ahead and pop over to the fun part, which is the actual, the visual demo. So what I have here is an image of all of the hospitals in the New York area. So these are actual hospitals with actual locations. We've generated either the surpluses or the shortages in this case. That data isn't publicly available, but we've done it sort of correlating with the various hospital sizes. So there's a couple features over on this thing. So first off, I'll point out that we can actually solve a much larger problem. We could take a look at all of the hospitals, on the Eastern Seaboard. So let's go ahead and zoom out here. You could do up to like maybe 1,000 hospitals, which is a pretty good chunk of the Eastern Seaboard. But again, because I'm doing this live, I'm going to stick to a smaller number that we can solve, in the couple minutes that we have here. The next thing that I can configure is the partition size. So this is the size of the pods of the hospitals that I want to consider. So in this case, I'm going to be grouping them into groups of 4. And again, we want these pods to be relatively contiguous. So we want them to be near these hospitals to be nearby so that we can make this sharing easy. The next thing I can configure is the number of neighbors that I want to consider. So, I don't want to necessarily link a hospital in the middle of New York with a hospital in the middle of Chicago. I can also tune the amount that I want to consider, either the distance or the cost versus the importance of making sure that all of them have a surplus. And finally, I can pick my solver and how long I want to run. So let's go ahead and run this on one of our hybrid solvers. So what's happening right now is this is being submitted to, the problem is being formulated, and this is being submitted to one of our online hybrid solvers available in Leap. As I mentioned, these hybrid solvers, this one specifically is our Leap hybrid sampler, which solves the same type of problem that our quantum computer solves. So it solves a binary quadratic model, otherwise known as QUBO, otherwise known as icing model. And here it is. It has solved that problem. It took about 10 seconds. It has a total utility of 504, a cost of 55. These numbers are sort of unitless, but you get the idea, with an overall energy of negative 134.9. And you can see that in this case, it has grouped the hospitals into these little groups of 4. You can see these sort of squares here, like so. And you can get a sense of how it did. So you can see that these hospitals are relatively close, and each block has a net surplus of resources, which is exactly what we were looking for. So just to complete this, let's actually run this on a different sampler. This time we're going to be running it on simulated annealing. Now, simulated annealing, for those of you that aren't familiar with it, is a classical algorithm. It's considered a competitor to quantum computers. Sometimes it does better than the quantum computer. Sometimes it does worse. And this particular implementation of simulated annealing comes with Ocean, which is our open source tools. So you can go ahead and try out your problems both on simulated annealing and on the quantum computer and on the hybrid algorithms, just the way that you would in any sort of benchmarking study. I'll mention that this simulated annealing is a good faith implementation of simulated annealing. It's not like, the best possible simulated annealing ever written, but it's pretty good, and we use it, often in our benchmarks internally. But in this case, unfortunately, simulated annealing was not able to find a feasible solution to this problem. Sometimes it succeeds, sometimes it doesn't. Live demo, in this case, it didn't. I'll run it on one more, which is our Taboo sampler. This is another competitor to quantum computing. It's similar to simulated annealing, although in this case, Taboo, it prevents the annealing path from walking backwards. So again, it's another classical algorithm that we've included in Ocean for the purposes of comparison with the quantum computer, because again, if classical is useful for you, then we want you to use it. I mean, why not? So in this case, we can see that it took about 13 seconds, and it found actually a worse answer than the hybrid algorithm did. It found a decent answer, but not as good as the hybrid. And so, this isn't a benchmarking study. Kathy McGew from D-Wave was giving a talk at this conference, which is going to be talking specifically about benchmarking. But I can say that, consistently, the Leap hybrid sampler is able to outperform these classical algorithms. And in general, we've seen, maybe 100 times speed up on this specific problem relative to these classical algorithms. So this is a practical problem available to you today that you can use both hybrid, or you could, if this problem is small enough, you could try solving on the quantum computer or our classical algorithms. But by using hybrid, you're able to get the best of both worlds, which is really what we all want, right? So I'm going to head back to my slides now. And so I just want to finish by saying that by using, to summarize, that by using both our hybrid systems and our classical systems, we are able to get the best of both worlds to solve customer scale problems up to millions of variables, to solve practical problems today. Thanks you all for listening to my talk, and have a great rest of your conference.